Hello, students, teachers, parents, and science nerds. Hello, everybody, and welcome to Nutshelled Science, where we lay out the facts, the good, the bad, and the ugly. Today, we are going to continue our biology series by looking at the chemistry of life. Don't forget that there's a link for worksheets that go along with this video in the description. I just ask that you like and subscribe. I apologize for any mispronunciations ahead of time. I do my best. Okay, let's go. The nature of matter. Welcome to the microscopic world of matter, where tiny building blocks of the universe party together in an endless dance of particles and bonds. It's like a cosmic Lego set, but with atoms instead of bricks. Atoms, the universe's tiny building block. Imagine cutting a piece of chalk in half, then again and again, until you can't cut it any smaller without it ceasing to be chalk. Congratulations! You've reached the atomic level. Each atom consists of protons, positively charged particles chilling in the nucleus, deciding the atom's identity. Like the bouncers at an exclusive club. Neutrons, the neutral peacemakers, adding mass but no charge drama. Electrons, tiny, energetic particles zipping around the nucleus like bees around a hive. Elements, atoms with attitude. Elements are pure substances made of only one type of atom. Think of them as the different flavors in the periodic table's ice cream shop. Gold, oxygen, carbon, helium, each with its own unique personality. What makes an element unique? The number of protons. That's like an atom's name tag. If you change it, you're not just changing its mood, you're creating a whole new element. Isotopes. Same element, different weight. Isotopes are like identical twins. They have the same number of protons but different numbers of neutrons. Some are stable, chill, and relax. Some are radioactive, ready to decay like an expired carton of milk. If an isotope is unstable, it breaks down over time, releasing radiation. It's nature's way of saying, I need a makeover. Compounds. When atoms form alliances, atoms don't like being alone, so they form chemical bonds to create compounds. These bonds come in two main flavors. Number one, ionic bonds. One atom steals an electron from another, creating oppositely charged ions. These opposites attract, forming a strong bond, kind of like an atomic love story. Example, table salt. Sodium gives up an electron, chlorine takes it, and bam, salt is born. Number two, covalent bonds. Atoms share electrons like best friends splitting a pizza. This creates a stable molecule that doesn't break apart easily. Example, water. Oxygen and hydrogen share electrons, forming the most important liquid on Earth. Molecules, the smallest units of compounds. When atoms bond covalently, they form molecules, the smallest units of compounds that still act like the full-size version. It's like a tiny sample size of your favorite shampoo, still the same thing, just smaller. Van der Waals forces, the weak, flirty attractions. Even molecules experience brief attractions due to van der Waals forces. These are weak, temporary forces that happen when electrons momentarily cluster on one side of a molecule, creating a tiny dipole. Think of it like a passing crush, short-lived, but sometimes significant. A static shock when you touch a doorknob. Even though van der Waals forces are weak, they add up, helping geckos stick to walls and allowing molecules to interact in complex ways. Why this matters? Matter. Everything around us is built on these atomic interactions. Without atoms bonding, we wouldn't have water to drink, air to breathe, food to eat, stars to gaze at. It's a beautifully chaotic dance of particles, forming everything from the oxygen in your lungs to the gold in your jewelry. So next time you look around, remember you're literally made of stardust, properties of water. So let's dive into the fascinating world of water, a molecule so essential and quirky that it deserves its own stand-up routine. The polar personality of water. Water is like that friend who can't decide whether to be positive or negative. With its oxygen atom hogging electrons like it's the last slice of pizza, the oxygen end becomes slightly negative, while the hydrogen ends are left slightly positive. This uneven charge distribution makes water a polar molecule, much like a magnet with distinct poles. Hydrogen bonds, water's social glue. Thanks to its polar nature, water molecules are social butterflies, forming hydrogen bonds with their neighbors. These bonds are like the secret handshakes of the molecular world, not as strong as covalent or ionic bonds, but crucial for water's unique properties. Cohesion and adhesion, water's sticky situation. Water molecules love to stick together. Cohesion and to other substances. Adhesion. This dual stickiness explains why water beads up on surfaces and why plants can defy gravity by pulling water from roots to leaves. It's like water's version of a group hug and a high five at the same time. Solutions and suspensions. Water's mixing skills. Water is the ultimate mixologist. When substances dissolve in water, forming solutions, it's like they're blending seamlessly into the crowd. But when they don't dissolve and remain suspended, it's more like a chaotic mosh pit. Either way, water keeps the party going. The pH scale, water's mood ring. The pH scale measures how acidic or basic a solution is, ranging from 0 to 14. Pure water sits comfortably in the middle at pH 7 being neutral, but throw in some acids or bases, and water's pH can swing, much like its mood on a Monday morning before coffee. In summary, water is a versatile, polar, and socially adept molecule that plays a vital role in countless biological and chemical processes. It's the life of the party and the glue holding it all together, literally. Cheers to H2O. Carbon compounds. Now, let's embark on a lighthearted journey through the world of carbon compounds, where carbon is the social butterfly of the periodic table, mingling and bonding to create life's essential molecules. Carbon, the versatile socialite. Carbon atoms are like the ultimate connectors at a party, each with 4 valence electrons ready to form strong covalent bonds. They can link up with various elements, hydrogen, oxygen, phosphorus, sulfur, and nitrogen, to create a diverse array of compounds. More impressively, carbon atoms love bonding with each other, forming chains and rings that serve as the backbone for complex structures. No other element matches carbon's versatility in building life's molecular architecture. Macromolecules, the Fantastic Four. Life's complexity arises from 4 major groups of carbon-based macromolecules, each playing a unique role. 1. Carbohydrates, the energy providers. Monosaccharides, simple sugars like glucose, the quick energy snacks for cells. Polysaccharides, complex carbs like starch, serving as energy reserves or structural components in organisms. 2. Lipids, the hydrophobic hero, comprising fats, oils, and waxes. Lipids are the water-fearing molecules that store energy and form protective barriers, like cell membrane. 3. Nucleic acids, the genetic scribes, DNA and RNA. These nucleic acids are the blueprint keepers, storing and transmitting genetic information essential for growth, reproduction, and function. 4. Proteins, the multifunctional workhorses. Made of amino acids, proteins perform a plethora of functions, from catalyzing reactions as enzymes to providing structural support and regulating processes. In summary, carbon's ability to form diverse bonds leads to the creation of these 4 macromolecule groups, each integral to the tapestry of life. So, next time you enjoy a slice of bread, marvel at the genetic code, or flex a muscle, remember the versatile carbon atoms making it all possible. Chemical reactions and enzymes. Finally, let's dive into the world of chemical reactions and enzymes, where molecules mingle, bonds break, and catalysts keep the party going. Chemical reactions. Molecular mix and mingle. A chemical reaction is like a molecular dance party where substances, reactants come together, bonds break, new bonds form, and voila, new substances emerge. For instance, when iron meets oxygen, they form iron oxide, commonly known as rust, nature's way of giving metal a reddish-brown makeover. Energy changes, the party starters. Just like some of us need a caffeine boost to start the day, chemical reactions often require an initial energy kick, known as activation energy, to get going. This energy investment allows the reactants to overcome the energy barrier and transform into products. Some reactions release energy, exothermic, making things warmer. Think of it as the reaction's way of saying, let's turn up the heat. Others absorb energy, endothermic, cooling things down like the reaction is putting on shades and chilling out. Enzymes, the catalytic cheerleaders. In the bustling world of cells, enzymes are the unsung heroes. Biological catalysts that speed up chemical reactions without getting consumed in the process. They lower the activation energy, making it easier for reactions to occur, much like a matchmaker who brings compatible partners together faster than they would on their own. The enzyme substrate complex, a molecular handshake. Enzymes have specific active sites where reactants known as substrates bind. This binding forms an enzyme substrate complex, facilitating the chemical reaction. It's akin to a firm handshake that initiates a deal, ensuring everything proceeds smoothly. Factors influencing enzyme activity. Keeping the enzyme happy. Enzymes are picky about their working conditions. Factors such as temperature and pH can influence their activity. For example, a change in pH can alter the shape of an enzyme, affecting its ability to bind substrates, much like how a bad hair day can throw off your whole routine. Real-world application: enzymes in action. A classic example of enzyme activity is the breakdown of hydrogen peroxide, H2O2, into water and oxygen. The enzyme catalase facilitates this reaction, preventing the accumulation of harmful H2O2 in cells, a bit like a molecular janitor cleaning up toxic spills. In summary, chemical reactions are the transformative events that drive life's processes, with enzymes acting as the efficient facilitators, ensuring these reactions occur swiftly and precisely. So, next time you enjoy a slice of bread or take a deep breath, give a nod to these microscopic maestros orchestrating the symphony of life. Okay, let's end this thing with a recap. Atoms are the universe's tiny building blocks bonding together in a cosmic Lego set to form everything we see. Elements, like different ice cream flavors, each have unique personalities based on their proton count. Isotopes are like atomic twins, with some staying stable and others decaying like expired milk. Atoms form compounds via ionic, electron-stealing, or covalent electron-sharing bonds, creating molecules. The smallest units of compounds, water, the quirky life giver, sticks together via hydrogen bonds, climbs plants, and plays mixologists with solution. Carbon, the social butterfly, builds life's essential macromolecules: carbs, lipids, nucleic acids, and protein. Meanwhile, chemical reactions are molecular dance parties needing activation energy, a caffeine boost, to start. Enzymes, the matchmakers, speed up reactions, ensuring life runs smoothly. So, whether you're sipping water, breathing oxygen, or flexing a muscle, remember it's all thanks to atoms partying in perfect harmony. There you have it, folks. That is the chemistry of life nutshelled. Thanks for stopping by Nutshelled Science. I will chemically react in a very positive way if you go nuts on those like and subscribe buttons for me. And I'll see y'all next time on Nutshelled Science.